All right. Okay. So wait, are you going to have to get those in on the shot too? Like, or wait, what are you?
He goes kind of like in portions, so he can actually. I mean, now that I have seen what he does, he goes in the portion that you are right now,
Mm-hmm.
and when you start writing, he follows you kind of.
All right.
So yeah, no matter where you are or where you're writing, I'll get the shot.
Okay.
So don't worry about where the shot is. More
Right.
worry about just make sure your body's not covering up what you're
Right. Yeah.
working on.
Yeah, I was just thinking about the aspect like.
Oh no, it's fine right now.
Oh,
It's
okay.
actually perfect.
All right.
This room has great light and everything. So.
Okay. So whenever.
Yep, whenever you're ready.
All right. So just let me just go over it. My name is Evan Waits. This is Math 219, Multivariable Calculus. As always, if you have any problems that you want us to do, feel free to post in the forums, and we can do those problems. So today we are going to be talking about cylinders and quadric surfaces. We are going to try and find the traces of. Okay, so. Our objective is to find the traces of the given surfaces in the planes parallel to the coordinate planes and identify the surfaces of these two equations. So at this time, I'm going to step off, and if you guys want to pause the video now and attempt these problems, go ahead, and then after you unpause, I'll come back and I will do them myself. So yeah, step off, do the problems. Okay. And then, yeah. And then this concludes. Again, if you have any problems, blah, blah, blah. Thank you very much, and that's it. Okay. All right. So hello, my name is Evan Witz. This is Math 219, Multivariable Calculus. We're going to be going over some practice problems today in cylinders and quadric surfaces. As always, if you have any problems that you want us to take a look at, feel free to post them in the forums. As long as they're not on your in-class activity packets, we will be more than willing to attempt them. So for this subject, we're going to be finding the traces of the following surfaces and then identifying the surfaces themselves. So we have two separate equations. We want to find their traces, and we also want to find what the surfaces themselves represent. So at this time, if you want to pause this video and you want to try and figure out what those traces and what the surfaces are yourself, feel free to do so. I'm going to step off for a second, and when you come back, I will solve them. So yeah. Okay, so the first equation that we're going to try and solve for the traces and the surfaces of is this equation right here. X squared plus z squared minus y squared is equal to -1. So the first trace that I'm going to do, so xy trace. So this is a trace where x and y can both be variable and z is held constant. So if I go ahead and plug z equals constant in here, we get x squared plus z squared, x squared plus k squared minus y squared is equal to -1. X squared minus y squared is equal to -1 minus k squared. Now, if you notice on the right-hand side, we have a term that's always going to be negative. This doesn't really matter too much. You can just flip the signs on everything by just multiplying both sides by -1. This equation right here is the form of a parabola. Whether the left-hand side, which is the difference between two squared variables, is equal to a positive or a negative constant, it's a hyperbola. So this trace is a hyperbola. Similarly, if you go ahead and take a look at the, let me think about this for a second. If you take a look at the yz trace, you end up coming up with the equation, so x is equal to a constant this time. You end up coming up with the equation, let's see, z squared minus y squared is equal to 1, or negative 1 minus k squared. And again, positive or negative, it doesn't really matter. This is the equation of a hyperbola, well, unless that is equal to 0, but that's a special exception. So this is the equation of hyperbola. We have that this trace is a hyperbola. And lastly, if you go ahead and take the xz trace, so this time y is going to be held constant. Plug that in, you end up getting that x squared plus z squared is equal to negative 1 plus negative 1 minus, no, plus, sorry, plus k squared. And for k greater than or equal to 1, this is a ellipse, so we go ahead and say that the traces are an ellipse, are ellipses. So now the tricky thing, so now we have to identify what surface this is. The tricky thing about these particular types of surfaces where each of the x, y, and z terms are all squared is that the hyperboloids of one sheet, hyperboloids of two sheets, and cones all have the same exact identical traces, and we need to figure out exactly which of those three equations which one of those three categories of equations this particular equation falls under. So in order to do that, we're going to want to get this into a more standard form of a quadric surface. So I'm just going to go ahead and erase a little bit here to make a little bit of room. So the standard form of these particular types of equations where x, y, and z are all squared is that you keep x, y, and z on one side, but you want a positive constant on the other. And right now we only have negative 1 on the other side. So in order to get rid of that, I'm going to go ahead and multiply everything by negative 1. End up getting y squared minus x squared minus z squared is equal to 1. So because there are two minus signs, okay. So because the variable terms are equal to a positive constant, and two of the variable terms have a negative coefficient, we know that this is a hyperboloid of two sheets. Two sheets. So an easy way to remember which of the two hyperboloids it is just to take a look at the number of negative coefficients that you have for your variable terms. If one of them is negative, then it's a hyperboloid of one sheet. If another one is negative, then it's a hyperboloid of two sheets. Another way that you can sort of think about it is if you look at the ellipse trace right here, you can see that when k is equal to 0, so when you're actually on the xz plane, no set of points, x and z, will actually satisfy that equation because that would imply that x squared plus z squared is equal to negative 1, which is impossible for all real x and z. So the reason why that can help you identify which shape that your equation gives you is if you remember, a hyperboloid of one sheet sort of looks like a tunnel that gets wider as it goes out further and further, whereas a hyperboloid of two sheets has sort of an asymptote along one of its axes, along one of its coordinate planes. So if you end up getting a ellipse that is not defined for k equals 0, then that you know that it's a hyperboloid of two sheets. If you get a ellipse that is defined for k equals 0, if one of your traces is an ellipse and it is defined for k equals 0, then you have a hyperboloid of one sheet. And the last case where you have a cone is when this ellipse trace is x squared plus z squared equals k squared. So when k equals 0, there's just one point that satisfies it, which makes sense. The cone narrows down to a point, and then it starts widening back out again. A hyperboloid of one sheet narrows down to a small ellipse, and then it starts widening back out again. And a hyperboloid of two sheets just looks very strange. It sort of looks like two sort of hyperbolas, sort of like switching like that. It's very hard for me to describe with my hands, but that is the basic idea of how you can identify between all of these different hyperboloids and cones. So, yeah. So now for the second problem over here, we're going to identify the traces of this equation, and then we're going to identify what surface it is. So the first thing that we're going to want to do is identify the traces. So again, we're going to do the xy trace first. So that means z is equal to a constant. So if you go ahead and plug that in, you get 4 times a constant squared minus y squared over 4 minus x equals 0. And if I go ahead and add x to the other side, you end up getting 4k squared minus y squared over 4 is equal to x, which is just the equation for a parabola. This is a constant term over here. Don't let the squared fool you. And this is y squared, so you have x is equal to y squared. Let me make that a little bit bigger. 4k squared minus y squared over 4 is equal to x. So this is the equation of a parabola. Next trace we're going to look at is the yz trace. So yz trace. So this is when x is going to be equal to a constant. So if I go ahead and plug that in, end up getting 4z squared minus y squared over 4 minus k is equal to 0. Or in other words, 4z squared minus y squared over 4 is equal to a constant. And this is the difference between two squared variable terms. So as we know from before, this is the equation of a hyperbola. Yep. And lastly, if we go ahead and set z equal to a constant, or sorry, if we go ahead and set y equal to a constant, so this is going to be the xz trace. Plug y equals k in, you end up getting that x is equal to 4z squared minus k squared over 4. Again, this is the equation of a parabola. So we have x is equal to some constant times a variable term squared minus another constant. This is a parabola, so yep. And that's our third trace. Now for this particular shape, we can actually very easily identify what this shape is based on our traces. We have 2 traces are parabolas and 1 trace is equal to a hyperbola. So straight away we know that this shape is a hyperbolic paraboloid. And if you go ahead and verify this through the original equation, if I just add x to both sides, squared minus y squared over 4, this is a pretty standard form of writing a hyperbolic paraboloid. So this shape is a hyperbolic paraboloid. Okay. So that is how you identify the traces and the surfaces given by some equations for quadric surfaces. There are a variety of other quadric surfaces that you can go over, like we covered briefly a cone and a hyperboloid of one sheet in this section, but there are also elliptic paraboloids and ellipses, or ellipsoids rather, and a variety of other shapes. Basically, what you just have to do is identify the traces. If you identify the traces for 90% of these shapes, then you'll be able to picture in your head what these shapes are. For the hyperboloid of one sheet, two sheet, and cone, it's a little bit trickier, but if you just remember what I said about the ellipse, whether it's well-defined for certain real numbers or not defined or only well-defined for a single point, you can identify it via looking at it from that perspective, or by just setting the original equation up in some standard form. But yeah, the best way to get used to these is just a couple of practice problems, just practice identifying a couple of different shapes and eventually get the hang of what these shapes actually do look like. So yeah, so this concludes the Math 219 section on quadric surfaces and cylinders and quadric surfaces, mind. If you have any more problems that you want us to do, again, just post them on the forums and we'll be more than willing to take a look at them, provided that they're not problems in the practice set. And yeah, thank you very much.